Swayam Prabha. Digital India. Educated India.
We have looked at nodal analysis, which is a way of analyzing circuits in general, and it can be scaled to any size of circuits. It's a way of systematically writing down the equations for the circuit so that it can be solved by matrix inversion. Okay. Now, instead of starting from KCL at the nodes of the circuit, you can also start from KVL around the loops. Now, unlike nodes, loops are ambiguous. That is, you can take the same circuit and come up with two different sets of loops, okay, or multiple different sets of loops, which are all independent but different from one another. Okay, so what we'll be looking at is a particular variant of loop analysis which applies to only a subset of circuits. It is not universally applicable to all circuits, and that is known as mesh analysis. This is basically a variant of loop analysis for what are known as planar circuits. Okay, like I said earlier, let me take the graph of a circuit and show you how one can choose multiple different loops around which to write Kirchhoff's voltage law. So let's say this is the graph of a circuit. This means that each of these 4 points is a node and these branches contain some two terminal elements. Okay, so now let's say I could choose this loop, that loop, and this loop. Alternatively, we could also choose this loop, and this entire thing. Okay, so we need to write 3 loop equations for this circuit. These are 2 possible ways of doing it. There are more ways as well. Okay, given this, there is a certain ambiguity. Now this mesh analysis eliminates that ambiguity. Okay, this is only for convenience. We can do loop analysis in general for any circuits, but for a couple of reasons. Firstly, that nodal analysis is the more preferred one, and with all this ambiguity, loop analysis looks complicated. I will not deal with that. I will only talk about mesh analysis. Okay, now what are planar circuits? Very simply put, they are circuits which can be drawn on a plane, like a piece of paper or the screen that I am drawing on, without crossing branches. Okay, for instance, this particular graph, you see that no 2 branches are crossing each other, so this is definitely a planar circuit. Now the keyword here is that circuits which can be drawn this way, not how you choose to draw the circuit. For instance, the classic example is this. Looks like these 2 branches here are crossing each other, but I don't have to draw it like that. Okay, I could have drawn it that way. So this is also a planar circuit. Right, but take this circuit for instance. Now, so far this is planar. Let's say I connect a branch from this node to this node. Okay, you can easily see that however I draw it, it will have to cross another branch. So this is definitely not planar. So the mesh analysis I am going to describe will apply only to this type of circuits. Okay. Another way to think about it is that a planar circuit is like the map of a region, map of a country, which can be drawn on the plane, and you won't have boundaries crossing each other, right? So if we have this is like a map. Let's say this is a country, and you can think of it as having 3 different states, and any branch will be common to at most 2 of these regions, okay, or 2 of these states. Okay, so a mesh is a loop in a planar circuit which doesn't enclose any other loops. Okay, that is, for instance, this is a mesh, okay, consisting of these 3 branches, this one, and that one. Whereas this is not a mesh. Okay, because inside this loop you have another loop, so that is not a mesh. Okay, so basically it's a loop bounded by branches, but inside that there should be no other branches, no other loops. Okay, so you can think of the planar circuit as the map of a country, and each mesh as one of the states of a country. Okay, so now with these definitions you see that each branch, it belongs to at most 2 meshes. Okay, again redrawing the circuit, let's identify the meshes first. When you have meshes, there is no ambiguity at all. There is only one way to identify the meshes. That's the advantage of this. Okay, I mean, that's the simplicity of it. That's why I'm going to deal with that. Now, as I said, loop analysis can be carried out in general, but I won't do that in this course. So there are 3 meshes here, and you can see that, for instance, these outside branches, they belong to only one mesh. For instance, this branch belongs only to that mesh. This one belongs only to that one. This one belongs only to that one. Okay. Now you have this branch which is common to this particular branch, is common to this mesh and that mesh. Similarly, this one is common to this one and that one. So each branch belongs to either a single mesh if it's on the periphery, or it can belong to 2 meshes if it is the boundary between 2 meshes. Okay. Now, by the way, once you have drawn the circuit, identifying the meshes is unambiguous. Okay, you see each region enclosed by a loop of branches, and that's a mesh, and of course you just make sure that there are no further loops inside this loop. Okay, but the same circuit can be drawn in different ways, so that still gives you some ambiguity, but once you have drawn the circuit, there is no ambiguity about the meshes. What I mean is, let me redraw the same circuit in 2 different ways and also identify the branches. Let me name these 1, 2, 3, 4, 5 and also 6. And you see that the exact same circuit can be written as that. I'll number them the same. So now this is 5 and that is 6. The meshes here are these regions which don't contain any other loops. So there are 3 meshes consisting of branches 1, 5 and 4, that is this one, then 2, 5 and 3, that is that one, and 4, 3 and 6, that is that one. Okay, and in this, if I identify the meshes, this is how it's going to be. And now the meshes will be consisting of branches 1, 2 and 6, 4, 6 and 3, and 2, 5 and 3. So they are different meshes. Of course, you analyze it using these meshes or those meshes, you will get exactly the same answers, but the intermediate variables that you have used in the circuit will be different. Okay, so you have to assume that the circuit is given to you in some way, already drawn properly as a planar circuit, and from that you identify the meshes without changing anything. Okay, that's the definition of a planar circuit and meshes. So using mesh currents as variables, okay, with nodal analysis we chose node voltages as variables and solved for them. In mesh analysis we will use mesh currents as variables and solve for those variables. From that we will be able to get all the other currents in the branches. We will be able to get the currents in all branches, and from that voltages in all branches using element relationships. Okay.